Hi and welcome to part 2. In this part we're going to talk about the sequence recognizer example, and this is where it gets real and we actually get a chance to apply some of our sequential circuit design techniques. So in this example we need to recognize the sequence 1, 1, 0, 1. And remembering from what we talked about in part 1, it's possible to have a sequence such as this one here with lots of 1s and then a 0, 1 that actually does contain that subsequence 1, 1, 0, 1. That's the one that we actually require. So we need to have a sequential machine to remember the first two ones that have occurred and then to check each of the next symbols that are received. So another example would be this sequence, which contains the required sequence as the first few digits, and then it also contains it here as well. And for this example, this is actually acceptable. Both of these would classify as the sequence being recognized within that larger sequence of binary values. And so in this case, this middle one is in both subsequences. For this example, we need this sequence to be recognized each time it occurs in the input sequence. So in order to recognize this 1, 1, 0, 1 sequence, we're going to define some states for this sequence. We're going to assume we start with the first symbol. We're going to call that initial state A. This is an arbitrary designation. We could just as easily call it X or T or some binary value, and we will talk about the way we decide upon the unique binary mapping of these states at a later stage. But at the moment, let's just call it state A. As each symbol in the sequence is recognized, we continue through these state transitions and we will output a 1 to mean that the full sequence has occurred. Otherwise, we're continually producing an output of 0. So from this initial state A, if we get a 1 input, then we have a 0 output, but we move to state B. State B is another arbitrarily named state. State B represents the fact that the first 1, that 1 is like this, in the input subsequence has just occurred. The output of 0 means that the full recognized sequence has not yet occurred. Now we'll add another state. We'll label this one C, and we get to C by having a 1 and moving from A to B, and another 1 and moving to C. If we're in state C, it means the previous two inputs were both 1s. Now, if we continue this logic on, we have A, B, and C, finally a state D, which happens after we've had the sequence of 1, 1, 0. And finally, when we're in state D and we have an input of 1, we have this output of 1. Always before, notice that the output was 0. In this case, we're using the Mealy model, since on the arcs we have the inputs and the outputs. As I said before, the output of 1 means that the sequence has been recognized, only occurs after we get a 1, 1, 0, 1. An interesting question is this one here. After we're in state D, after having an input of 1 and we get an output of 1, where should we go to? Should we go back to A? Should we go all the way back like this? Or remembering that we need to be able to recognize this sequence twice, given this much larger sequence of numbers, then this final 1 actually needs to be the first 1 of the next subsequence. So instead of moving all the way back to state A, we actually want to move to state B, because it's as if we have a single 1, and if we get a 1 again, we'll go to C. If we get a 0, we'll go to D. If we get another 1, then this is this sequence recognized again, and we should have an output of 1. So thus clearly the final 1, this one here, is actually part of the second subsequence, and it also follows a 0, which is not a subsequence of 1, 1, 0, 1. If we had a 0 here that we were trying to recognize, then it would be, but if not, then we really only count it as that first step. So after D, getting a 1 should mean that we get the same state reached as the initial state we got after the first 1 was received. That is, we were in A, we got a 1, we moved to B. So therefore the state diagram starts to look like this. We actually have the arrow going back to B. So then for this state diagram, the states have the following abstract meaning. A means that no proper subsequence of the sequence has occurred. B means the subsequence of 1 has occurred, obviously moving from A to B, there's been a 1 input. C means the subsequence of 1, 1 has occurred. So to get to C, we've had a 1, another 1. Then for D, the subsequence 1, 1, 0 has occurred. Just looking at these inputs, 1, 1, 0 gets you to state D. And then the input 1, output 1 on the arc from D to B, that is here, means that the last one has occurred in the sequence, and thus the sequence is recognized. And we also are part of the way into the next sequence, as in we're at B. So here's something you should pause the video and try and do yourself. Think about what arcs are missing. When we're in A, 1 input. When we're in B, 1 input. When we're in C, 0 input. When we're in D, and a 1 input. So we have to write in the other arcs. So you should do that. And the answer is we need an arc from A back to A when we have a 0, giving an output of 0. So for B, if we get a 0, we obviously don't stay at B and we don't move to C. We have to go back to A with an output of 0. When we're in C, if we have an input of 1, then we actually stay in C with an output of 0. Because you think about it, if we get a 1, then it's like we've had a 1, 1, 1 in a row. Then it's the same really for the purposes of our sequence of having a 1 and a 1. Maybe to make it a little bit clearer, that would be as if we got a sequence of say 1, 1, 1, 0, 1, then that would actually fulfill our criteria because of this part here being the actual sequence we're looking for, 1, 1, 0, 1. So it's like we've moved from A to B with this, B to C with this, but actually we may as well stay at C because we're 2 symbols into the sequence. Then from D, if we get a 0, we don't stay at D, we obviously move all the way back to A with an output of 0. So here the state transitions are drawn up a bit more cleanly, and then this note here is what I was explaining before about having the 3 1s in a row for the purpose of our state diagram is as if we've just had 2 1s in a row of the sequence. So C means that 2 or more 1s have occurred in a row. Now from this state diagram we need to fill in the state table. This is another exercise which I suggest you pause the video and do. So there are 4 states. Given that we're using a merely state diagram, these are A, B, C, and D, written in the table A, B, C, and D here, then the question is, what's the next state given an input of, for example, x equals 0? So if we're in A and we get x equaling 0, then we stay in A. If we're in B and we get x equaling 0, then what happens? Then we move from state B back to state A. If we're in C and we get a 0, then we move from C to D. If we're in D and we get a 0, we move all the way back to state A. If we're in B and we get a 1, so we're in B and we get a 1, we move to C. If we're in C and we get a 1, then we stay in C. And if we're in D and we get a 1, then we move back to B. In terms of the output, out of all of these, the only output that's a 1 is this one here, and that's when we're in state D and we get a 1. So that is, we're in state D and we get a 1 just here. All the others will be 0. Okay, so we've now determined the state table and the state diagram for the merely case, that is, where the output depends upon the state we're in and also the input. And the question is, what would the state diagram and state table look like for a more model? And just intuitively, we know that more model usually has more states because we're going to need another state that we can have an output of 1 for. In this next exercise, we're going to go through and do the same formulation for the more model case. So remembering that for the more model, the outputs are associated with states, we're still looking for this sequence 1101. We need to add an additional state, which we're going to call E, which has an output value associated with it. And you'll see this new state E is very similar to B, and that will become more obvious when you actually see the diagram. Once again, reminding you, more model for the sequence recognizer usually has more states than the merely model. Okay, so we've added this red state E here. The rest of the diagram is basically as is, apart from previously when we went from D and we had a 1 input, then we had an output of 1, but we also moved back to B. And if we had an input of 0, then we moved back to A. The difference being that since we need a new state E to have an output 1 associated with it, where B only has a 0 output associated with it. But notice from E and from B, whatever the input combination is, the next state is the same. So if we're in B and we get a 0, we move back to A. If we're in E and we get a 0, we also move back to A. If we're in B and we get a 1 input, then we move to C. If we were in E and we had a 1 input, then we move also to C. And so we would say that these states, that is B and E, do represent a different abstraction of the input history, since the input history to get to E requires us to have the full sequence 1101, whereas to get to B, then you have to have been in state A before. There's no way to move to state B from any of the other states. So here's the state table for the Moore model, and we can see we've got this additional present state row E, and we've also got this next state moving to E. Apart from that, the rest of the table is all the same. All of the present state, next state combinations are the same, and it's only when we get to state D and we get an input of 1, x equaling 1, like this, then we move to state E, where before we moved to state B. And then when we're in state E, then you notice that the next state is the same as B. This next state here is the same as the next state for E, given an input of 0 or 1, and the difference, of course, is the output. For B, the output is definitely 0, and for E, the output is definitely 1. Alright, so now we've looked at the Moore and Mealy models for this sequence recognizer example, but up until now we've been using the symbols A, B, C, D, E to represent the states, but we need to have a binary code for each of these states. We have a mapping between the state symbol A and then some sort of binary value, and the question is, how do we choose those binary values? In the next part, we'll be talking about the state assignments, particularly whether we should use a normal binary counting order or a gray code counting order. And we'll go through an example and look at the difference in terms of the optimization for both of these two options. And then in part 4, we will actually look at a further state assignment called one-hot assignment. So I'll see you then.